All right. Good morning, everyone. Good morning, Ryan. Ryan, I'm putting up a video about the problem you sent me. So I will have that recorded this evening and placed up there. If you're still working on it, and up there for everyone. Also, Heather had a question on a problem in the problem sets, and I want to record those separately and attach them to the playlist here. I was doing them in here, and I think people were having a hard time getting to the information, so I'm going to record them separately. Today's not going to be too terribly long. We're working our way through in the paper textbook, the last chapter, and we are flipping to the page here. We're on section 2. We're dealing with exponents and laws of exponents, and we're going to try to use those laws of exponents. And we're going to finish up scientific notation today, and then for the next 3 classes, we're going to talk about polynomials. Section 3 and 4 will be Wednesday. Section 5 and 6 will be Monday, week from now, and section 7 will end on the following Wednesday. So today's stuff isn't too terribly intensive. Again, I would suggest I have the worksheets posted up, and that way we would do the worksheets in class. Please look at those worksheets on Blackboard. And if you need a copy or having a problem getting to Blackboard, email me. Just email me. Let me know what's up. And we can adapt. Email communication in this class has been immensely good. In other classes, it's been a little spotty, and so we play with things after the fact. What we're going to do is we're going to look at probably one of the more useful things to come out of the rules of exponents. But first, I'm just going to jog our memory, because these are relatively new things for us. What we mean by an exponent: we have some base to a power. So that's a base. Whoops. Base is B, not P. And it's multiple multiplications. In fact, n is the number of times we multiply. So, this is the equivalent of b n times. And so these multiple multiplications are what lets this happen. This gives rise to some rules. If we multiply something 0 times, there's the initial number 1 hiding in the front of our multiplications. If we multiply something 1 time, it's itself again. If my bases are the same, and I'm multiplying 2 exponents, I can add the exponents to get my result. And multiplication has its friend division. So if my bases are the same, and our key is always the bases are the same, if I'm dividing, I subtract the exponents. If I take my base to a power and I raise that whole thing to a power, I multiply my exponents. And I'll show you the corollary, though we rarely use it in here. If I take the nth root of something, I divide my exponents. If I have 2 different bases and collectively they're taken to a power, that power distributes. Right, that P gets applied to each of those. And I need my inverse rule now. Whoops. Almost wanted to switch over to A's there. Something has a negative exponent, it pushes it to the other side of the fraction bar. So I'll write both examples. And these are the rules that we're going to be playing with here. One of the useful things that comes out of this is a thing called scientific notation. And scientific notation is a way for scientists to deal with large numbers without having to focus on more than what was needed. And I guess I'm really going to have to explain that. It has two parts, a mantissa and a power part. And let me write one and go from there. So these are the rules that we're going to keep coming back to. Okay? And that's on the first worksheet, and we want to practice these exponent rules. But what we can do is we can write any number as some base times 10 to a power. If this A part whoops, there's no equal, is between 1 and 10, but it won't be 10 again. And I'll show you what it means. What this lets a scientist or someone measuring do is it puts all of your accuracy or all of your precision into the A part. So for example, if I am measuring something really big, let's say kilometers or meters, we'll do meters, and I'm doing 32,500 meters. It implies by the zero here that I can't measure any better than the 100 place, right? Because if I were going out and counting meters, it's very rare to get an exact number of them, right? And so whatever measuring instrument I have is good up to 100 meters. And so when we write a number like that, it implies it. Well, that means these zeros are extra information. So a scientist would go, well, if this, let me change it. No, I'll leave that. If the 325 is what matters, I'm just going to worry about the 325. Times 10 to the fourth. Well, this is the same number as this. But we call this scientific notation. And I'm going to get to how we figure out each part. I want to introduce the concept and its utility. It becomes very useful. Before calculators, scientists had to calculate very large numbers by hand, and so anything that would make it easier to do was used. And there were three techniques that were commonly repeated. One was a slide rule, which needed tables to look up particular values. Scientific notation was the other, and then memorization of especially square roots and certain functions were the three techniques that scientists used to do their calculations. So you'll hear a lot of the times when especially if you're doing things within nursing, your significant figures, how much of the measure matters. And here, this shows there's three significant figures. There are three numbers that matter to the measurement. The rest of this information tells me how far over I am. So let's look how I pulled this number into scientific notation. What I did was my number A has to be between 1 and 10, and it can't be 10. So 3.2 is a number between 1 and 10. And then I count how far I have to move the decimal place. 1, 2, 3, 4 to get back to my original number. And that's my power. Remember when we were multiplying decimals and multiplying large numbers, the number of zeros was related to the number of zeros in our number. And so each place is a power of 10. And I'll show you what I mean here. And I wrote this when I wrote our places, so let me scroll down here. When I was talking about the ones place, that was 10 to the 0. I was talking about the tens place, that's 10 to the first. Talking about the hundreds place, that's 10 squared. And the thousands place, 10's cubed. When I'm talking about the first place beyond the decimal point, which is 1/10, that was 10 to the negative 1. And when I'm talking about 100th, it was 10 to the negative 2. And 1,000th is 10 to the negative 3. And I wrote this up and I said, we're going to see where this comes from when we do exponents. And that whole idea of having the negative exponent turning into a fraction, every number now can be written as a power of 10. So that you only talk about what you can measure. So that's accurately, I can measure 3 sig figs in this significant figures in this. And this tells me how big of the number I'm measuring. So let's look at a couple of these. And we need to go backwards and forwards. So for right now, I'm talking about taking a number as we normally write it and writing it into scientific notation. All right, so where's the example I want to use? And so we can look at this number, and when we get used to seeing it, 10 to the 4th is in the 10,000s. 10 to the 5th is in the 100,000s. In fact, every 3 we have a comma. So 10 to the 3rds is the thousands. 10 to the 6th is the millions. 10 to the 9th is the billions. So we have a visual clue onto how big the number is, and we know how many of the thing we're talking about. So let me I'll look at the one I like, the speed of light, because I was just watching a thing on the person who invented computer programming languages, Admiral Grace Hopper, and she taught my grandfather computers. He was in the first class in the Navy with Grace Hopper, and she had a thing that we knew about because our family had talked about it, but I didn't know how big of a thing it was until I watched this biography on her. Well, watched a few biographies on her a few years ago, but I've been continuing to watch. She gave 200 lectures a year all the way up until she died. Her thing was teaching, and there's beautiful 60 minutes coverage of her right before her death, where they were talking about, we're in the computer age, and she's like, we're just beginning. And she had a good clue of how strong and powerful computers would be. Because she used to walk around, and you talk about the thing that was slowing down the computers was how fast an electronic signal can travel. And the fastest electronic signal can travel is the speed of light. And so she had them make wires for a billionth of a second. And so a billionth of a second is 1 times 10 to the negative 9th of a second. That's a billionth. And light travels 1 foot in a billionth of a second. Now at the time, computers were running at a microsecond, which is 1 times 10 to the negative 6th of a second. And a microsecond is 1,000 feet. And so she would carry these wires that were 1 foot long and talk about this is a billionth of a second, and this is how we can get, save a billionth of a second in calculations. And then she would carry 900-foot wires and talk about this being, this is a microsecond, and every time we save this much, we save microsecond. In fact, during the last recession, the largest public works construction was a fiber optic cable from New York to Chicago, and they bought up the land because it was cheap coming out of the last recession to run as straight a possible cable between the financial institutions, so they could shave off microseconds in the transaction rate, so that they could do these microtransactions, which are all the rage right now. I have a friend that works in a Chicago hedge fund doing calculations, and this speed of light thing comes into this. But talking about, if I were to write 1 billionth of a second, I'd start with my 1 and my decimal places here. -9 says I have to move the decimal place over 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's where my decimal place goes. Each one of those little humps gets a 0. And that's how we would write a billionth of a second in conventional notation. So if I have 582 nanoseconds, which are billionths of a second, I would write 582, put my decimal place here, and I'd move over the 10 to the -9th. So let me rewrite this in scientific notation. It's 582 times 10 to the -9th. And so I move to the left 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And so this is why this notation is chosen. It's easier to write when dealing with small or very large numbers. Some numbers would be really, really weird to write. The mass of the sun in kilograms. Is 1.98 times 10 to the 27th kilograms. If I want to write this in scientific in standard notation, I write 1.98, and I go over 27. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I want to run out of room. I have too many zeros to write the mass of the sun. Right? And so this notation is portable. So to show the why, let's show some of the rules here. So since the powers of 10 talk about where I am in my place value, right? Our place value tells us where our decimal point is. So to convert from scientific notation, to a standard number, so let me grab an example one here, and then I'll write my steps off to the side. Let me go. I don't want a huge number. I want one that's slightly compact for us here. the book likes using really big examples to get used to it. I will put yeah, 4.87 times 10 to the 8th. Yeah, that'll work for me. All right, so to convert from scientific notation to standard notation. So this is scientific notation. Step 1. Write the mantissa, which is this front part, the part with the A in it. Remember, this is our power, and we're going to say specifically this is a power of 10. So I write 4.87. Okay, with my focus on, now I'm going to move the decimal point keeping space for zeros, because notice zeros were a thing that we're adding or removing with these powers of 10. Because what does 10 do? 10 gives you all your zeros, right? 10 to the 5th is 100,000. And so it gives me those 5 zeros. Well, in this case, I'm moving the decimal place. So A, if the power of 10 is positive, move right. If the power of 10 is negative, move left. And so what we want to think of is 10 to the 8th is a big number. I want to make this bigger. And bigger decimal place goes further to the right. And so I need to move this 8 times. 1, 2, 3, 4, 5, 6, 7, 8. That's where my decimal place is going to end up. Now I use humps. I've always done it like a camel hump. And so I put my zeros into here. And then I write everything back down. 1, 2. And I don't worry about having the decimal place at the end, but I do like every 3 digits putting my comma in. And so we have 487 million. Now, some things I've learned as we're doing these from a large number of time is the powers of 3 are your named numbers. And so this was 8. It's 1 before 10 to the 9th, or 1 before a billion. So I knew this was going to fill up the million space. But you'll see that as you do the patterns. The key is that you move the decimal place, the number in the exponent. If it's positive, you move to the right. Well, let's look at what we can do with a negative exponent here. So I'm just going to change color on a -1. I haven't used my bright pink in a while. I'll go back to that. 1.48 times 10 to the -5th. All right, so we're going to do the same rules. I write the mantissa down again, 1.48, and I move the decimal place, keeping space for the zeros. If the power of 10 is negative, move left. Well, this is a -5. So I'm going to go 1, 2, 3, 4, 5. And I get 0.0000148. Here's a dirty secret about negative decimal places. Because this moves the decimal place, and if we write scientific notation correctly, where this number is between 1 and 10, this will always have one skip before you start adding zeros. And so the number of zeros is 1 less than this. I added 4 zeros. 1, 2, 3, 4. Again, it's just something to look for. I can't say that about numbers that are bigger, that are positive, because I don't know how many decimal places. If this was 4.875, I would have gotten one less zero in here. So these are just patterns that you should pay attention to when you do scientific notation. So moving from scientific notation to normal notation, positive numbers move the decimal place right, negative numbers move the decimal place left. And you want to think about that large positive exponents are bigger numbers. So you want to take that thing between 1 and 10 and you want to make it bigger. And we do that by moving the decimal place to the right. Negative powers of 10 are small numbers. And so we want to make that number between 1 and 10 smaller. We do that by moving the decimal place to the left. All right, let's go the other way though. Let's go from standard form to scientific notation. And I'll start by writing a decimal. All right, so move the decimal place until you create a number between 1 and 10. Keep track of the number of moves. So I want to make this a number between 1 and 10, so I need to move the decimal place over to here, because that'd make 1.58. That's my number between 1 and 10. So I go move once, I move twice, I move 3 times, I move 4 times. So I want 1.58. Well, if you moved right, this is negative. If you moved left, this is positive. So I moved right, 1, 2, 3, 4. So that's 10 to the negative 4th. Let's go the other way. Oops, I'm going to change color again. Do that bright pink I haven't been using for a while. That's a comma, sorry. I have a really big number, and my decimal place is here, right? It's where it would be on the number line. I need to make this a number between 1 and 10. So I'm going to move my decimal place over to here so that I get a 3.283. So I move once, twice, 3 times, 4, 5, 6, 7, 8, 9, 10, 11, 12. You get 4.283 times 10 to the 12th, or 3.283 trillion, which is our latest stimulus packages, right? About 3 trillion or so. And so that's how we convert between the two forms of notation. But what makes this very, 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 very powerful is what's called order of operations. A lot of times the problems that we have, knowing about where we are in the problem helps. And so a lot of science courses start with things called powers of 10 calculations. But I'll show you what can happen here. I want to look at science. We have a lot of multiplications going on. Multiplication tends to happen a lot more than addition and subtractions. Additions and subtractions, scientific notation doesn't give us a great benefit for, but it really helps with the multiplications, divisions, and powers. So 5 times 10 to the 4th times 7.1 times 10 to the third is a multiplication. Now I'm going to think about this in its older terms. That's 50,000 times 7,100. I'm going to show you how scientific notation makes it go a little bit quicker for us. Well, these are multiplications, so I'm going to turn them for illustrative purposes into just a series of multiplications. Now, our property of real numbers told us that our order of multiplications didn't matter. A times B is equal to B times A. And how we associated didn't matter. Right? They're commutative and associative of property of multiplication. So, I can line these up any way I want. The way I'm going to, this is the decimal point on the 7.1. I'll try to put that down lower. So I will put the numbers that aren't 10 together. 5 times 7.1 times 10 to the fourth times 10 to the third. Well, what that does for me is these have the same base. My law of exponents says if I have two things with the same base, I can add the exponents. So I can add these exponents and I get 10 to the 7th. So that's the back half of my scientific notation. And 5 times 7.1 is 35.5. Look how much quicker that was than the long multiplication we did. This is why scientists use this. They knew their numbers would only be 3 to 4 significant figures. These numbers here wouldn't be that large because measuring precision is usually 3 to 4 significant figures. In a modern era, now that we have computers and extra utilities, we can get precision into 6 to 12 decimal places. And yeah, we got to go back to calculators for this. But what's really, really nice is most clinical applications, the medications that you're giving out, the machines that you're using, 2 to 3 decimal places is good. And so this speeds up the type of calculations you can do, because you can focus on multiplying these parts where this part is an addition. You've taken one part of the multiplication, you turned it into addition. It's keeping track of the number of zeros that you have. The only thing we need to do is, well, this number is bigger than 1. So I move my decimal place over once. That movement of 1, I have to add, right, plus 1 to that. And that gives me my answer. And so this is why there's a focus on scientific notation. It lets you do mathematics on numbers, particularly in scientific applications, quickly. And that's why it's taught, and it falls out of the exponent rules nicely that we look for these things coming through. I'm going to do another example here. I did a big number, so I guess I'll have to do a small number. Actually, I'll do mixed. I'll do something really, really big times something really, really small. So 8.6 times 10 to the 9th. So 10 to the 9th is a billion, so this is 8.6 billion. It's about the population of the world, roughly. And 4.4 times 10 to the negative 12th. Which is a very small number, right? 10 to the negative 12th is a trillionth of something. So, what could I say is a trillionth? I guess if I took a proton from every person in the world and stacked them up, this is how long they would be? Yeah, that's about right. Ish. If you want some realistic thing for it. But I have a really big number times a very, very small number. So I'm not going to rearrange these in order. I'm going to summarize. We took the things, the powers of 10, and we added the exponents. So 9 plus negative 12 is negative 3. And now I have the back half of my scientific notation. I add the exponents. All right, I'm going to scroll up here, because that's what, by rearranging this allowed us to do. It allowed us to add the exponents of the base 10 part. Well, I don't have to rearrange it for that to be true. I can add the base 10 part. And so the multiplication I need to do is 8.6 times 4.4. Right. 4 times 6 is 4. Carry my 2. That's 34. And so I get the same thing over again. Got 2 decimal places. So 37.84 times 10 to the negative 3. Again, this has to be between 1 and 10. So I'm going to need to move this over 1. 3.784. I'm going to add 1 to that. Right? Any movement to the left adds 1. Any movement to the right takes 1 away in this form. But this is much easier to write than what the equivalent would have been. This would have been 8 times that would have been what it looked like in standard form. And so this is why this notation is used for us. It's a way of focusing on the things that matter. Trying to, when we talked about the history of numbers and how numbers came together, there would have been cultures that would have written this. I'm trying to think what this would have been like in there's not a Roman equivalent, but let's look at Romans would have used, let's see, 8 billion. They would have done 86, so that's LXXXVI times C is 100, M times M. That's how they would have had to write it, right? 1,000 times 1,000 times 86. I'm missing 1,000 in there, aren't I? 1,000 times 1,000 is that? Yep. In Roman numerals, that they would have had to have written some concept of that. And there was no way of doing that math by looking at how they wrote it. People used to count sticks, count stones. When we started writing our numbers, 324, we started figuring out that place value underneath it all was saying this is 300 plus 20 plus 4, and we could carry that around and do operations on them. In fact, we're saying it's 3 times 10 to the second plus 2 times 10 to the first plus 4 times 10 to the 0th. Again, I hinted at you would see why, as we went on, why the exponents were in the background. Well, this let us focus on when you added things, you gathered things that had the same exponents together. Now we're starting to say, well, some of the things we write even in this form are too big. So we can strip it down and focus on the things that matter. The way we write numbers are for our convenience. And for most everyday things, our standard form of numbers convey as much information as we need. And they let us do arithmetic operations on them quickly and with some rules. those rules and the way we write them are not the number. They're for us. They're our convenience. Right? And there were points in history and points in culture where we did not write our numbers like this. Scientific notation is coming about in the age of science, where we started dealing with larger and larger numbers in how we wrote them, a way of writing it that lets us do quick operations on them. Let me show you some divisions also. So 9.6 times 10 to the 20th divided by 3.2 times 10 to the 12th. And again, we're looking at why this form of writing it this way lets us do things with it. So 9 to the 20th. Let's see if I can do this right. I'll just do it this way. 4, 5, 6, 7. I don't even have room for 10 to the 20th. Let's see. To the 12th is a trillion. So the 15th is a quadrillion. Quadrillion. 18th is a quintillion. So this is 960 quintillion. No, this is 960 hextillion. Right? Septillion would be next coming through. So 9 to the 18th is trillion, billion. Let me see if I get it right. Trillion is to the 12th. Quadrillion is 15th. Quintillion. Yeah, this is 960 quintillion. Large number. Divided by 3.2 trillion. I'm not doing the long division on that. But if I rewrite my division in fractional form, and I focus on front numbers and pull my exponents a little bit further away, my rule of division of exponents says I subtract. Remember? B over m over b over n. Sorry, my m looks very... I will say, writing on this is much smaller than a blackboard, and my hand, I think, is starting to get achy and sore. But we'll get there. So b m minus n. So these have the same base, so I can subtract exponents. So I know my answer is going to be somewhere around 10 to the 8th, around there. And then I do this division here. And I think that goes in 3 times. Okay. And so I get 3 times 10 to the 8th, which is about the speed of light. And there's a reason why, but I chose my numbers just so I could say, hey, the speed of light is 3 times 10 to the 8th meters per second. Just something, right? How far light travels in a second. But the point is we write these numbers this way so we get the advantage of our rules of exponents. And our rules of exponents let us work on these numbers differently. Well, let's use one more rule of exponents to show us how we can get some advantage from this. So, let's say I have a mathematical calculation where I'm calculating the area of something in square feet, and my feet are measured, I'll say, 1.3 times 10 to the 5th. So that's 130,000 feet in one direction. And it's a square. So I'm squaring that. Now our exponent rules said if I had 2 different bases to a power, it's the same as the first one to that power, the second one to that power. And so I multiply my this to that power. Well, this was to the first, so that's 1.3 squared times 10 to the 5th squared. But my power rule says that's going to be 10 to the 10th. Right? There's my n times p. And then 1.3 squared, I can plop on my calculator. I could possibly plop on my calculator if it powers up. Is 1.69. Should have known 13 squared is 169. Yeah, more coffee. And so this calculation happens a lot faster. And so if this was feet, then this would be square feet. But it's a way of doing large number calculations using these rules of exponents that we talked about last class to make the calculations go faster and to make them focus on the parts that matter, the number of zeros and the significant measure. All right. I want to show you one small thing about this that's going to lead into the next section, which are polynomials and how polynomials are similar to numbers. So I'm not going to add any variables yet. I'm just going to talk about, and I did it with the number 324. So I go to 324 plus 2,841. And I'm going to use the rules of scientific notation and how we wrote these things in expanded form to show something really nice. And we talked about it a little bit a few classes ago, but I'm going to try to bring it all together here. Right? This is how we're going to try to end all of this. So this is 300 plus 20 plus 4, and this is going to be plus 2,000 plus 800 plus 40 plus 1. Right? Writing it in expanded form. But I'm going to use scientific notation to help us here. So this is 3 times 10 squared plus 2 times 10 to the first. And I know, I say to help us, I know you can do this in standard methods. What I'm trying to do is pull out a pattern we're going to use again, right? So I'm not saying do it this way. I'm saying there's something happening underneath the hood here that we want to pay attention to, because I'm going to use that mechanism to do some more stuff, right? So I'm not saying, oh, we have to add numbers like this. I just want to show you something that happens behind it all, so that when we do these polynomials, we can borrow this idea. So 4 times 10 to the 0 plus 2 times 10 to the third plus 8 times 10 squared plus 4 times 10 to the first plus 1 times 10 to the 0. So what I've done is I've written it as some number times some power of 10. And what comes out of this is when we added things, I can't add 3 times 10 squared plus 2 times 10 to the first. And it comes from, let me see if I can do it here. We had this rule. If these parts are the same, if one part of the number is the same, I can go backwards. And so let me rearrange these so I have same parts together. Same versus same versus same. So I think my biggest part is 2 times 10 to the third, so I'm going to put that out front. And then I have 10 to the, so I have 3 times 10 to the second. Where's my other plus 8 times 10 to the second. Plus 2 times 10 to the first, plus 4 times 10 to the first. I'm gathering all the little bits and writing them in order. And that poor lowly 1 just keeps scrolling over there. 1 times 10 to the 0. Let's look at just these two right here. All right, now I'll use different colors. Where's that pink I keep avoiding? Whoops. I went right over the number I wanted to show. I'm gathering together pairs that share the same power of 10. Well, if again, I'm just going to focus on this yellow bit here, pull the 10 squared out front. If I take this and realize this is multiplied by something and this is multiplied by something, and you get the 3 plus 8. Right? There's a 10 squared and a 10 squared there, just like there would be an A here and an A here. So I pull the 10 squared out front, and I have 3 plus 8, or 11 times 10 squared. Well, what do I do when I add those points, right? I add the 11, and I carry the 1. There's my 11. Well, I'm going to turn that to 1.1 times 10 to the third. I've just carried my 1. Right. So underneath the hood, we were using exponents and we were doing exponent additions. But the thing that's really, really neat for us here is we could only add things where they were multiplied by the same part. And that's why we aligned them up in columns, because each column represented multiplying by the same part. Well, we're going to, I want you to come down here. We're going to find a new way to maybe say 2x cubed plus 3x squared plus 8x squared plus 2x plus 4x plus 4 plus 1. Notice I've replaced 10 squared with x squared. I've just turned it into a variable. And this lets me gather the things that have the same term of x. And we call this like terms. And this thing here is called a polynomial. Many names, polynames, and each one of these is a different name. And what we're going to do is we're going to compare it to what we do with numbers, but we're putting a variable in there, and we're putting a variable to a power. But that's what we're going to work on next. I strongly recommend the worksheets for the chapter 15, I think, that I posted on Blackboard, working on the first 2 sections of that, getting comfortable with the rules of exponents and scientific notation. I would read section 3 in the book with polynomials, because that's what I'm going to talk about in the next class. But I continue to work on the homework and the worksheets, and continue to email me questions. I am going to meeting at 12:30, but after that meeting I'm going to record the videos for the questions that Heather and Ryan asked, and then I'll place those up on the feed. Please double check the feed for anything going through. All the work that is due is on Pearson now. Does anyone have any questions or anything? You guys are usually really good at asking questions. Today you were very silent. And I know the chat thing's weird. I know this stuff's odd because it's extending the notation that we've used before. And I think it is the most modern extension of mathematical notation. Again, the notation is for our benefit, and I'm just trying to point some things underneath the hood. But this is where we're going on Wednesday's class, is going to be these polynomial things. But they're going to be very similar to some of the patterns we had in numbers, except we don't know what x is, so that gives us a little extra twist, right? And I know we all like to know what our x is, right? So, all right, practice those worksheets. Keep asking me questions. Be safe, be well, everyone, all right? Yeah, no. put in words May 11th, which is last day of classes. Email me any questions and any deadline issues. Really hope to see you guys again. Take care.